guys for being here again today for this yet another session of the periodic seminars. Today we have a talk from Claro on the scalability of constructive interference in local wireless networks. He has around 45 minutes to entertain us. Thank you.
Okay, good morning everybody. I'm looking forward to see if I can really entertain you. So what I'm going to be talking today is a work that I have been doing for a few months, last year, right? Maybe like 8 months. And we have looked into, there is a very interesting technique in low power wireless networks and in wireless networks in general, which is if you want to make more than one transmitter transmit at the same time and the same information concurrently. It is expected that the information that you transmitted is the same, they can add up constructively in the receiver. But that is not always the case, and you will understand that for that to happen, there is a set of parameters that have to be tuned appropriately. And we're going to be looking into that today, in particular how it is used in sensor networks. This is a work that was done in collaboration with other institutions. In particular, I will go into more detail in the presentation, but it's basically Portugal, the International Center for Theoretical Physics in Trieste. They have a laboratory which works specifically on wireless networks, and also we have a collaborator from Etis Research. So let's start on radio propagation. So this picture here is showing a floor map, and then this is the numerical solution of the Helmholtz equation, which shows the energy density of a radiator. You can think of this as a transmitter antenna. And the color in the scales indicates the intensity of the wave on the spatial distribution of the intensity of the wave. So you can see that if we were in open space, you will expect that wave to propagate through the space smoothly, and you will see the intensity decaying with distance, but in a homogeneous way. On the contrary, when you are in an indoor environment like here, there is reflection of this wave in the roof, in the walls, and so forth, and what we get is something like this. So that is bad news if you want to use a wave that is propagating like that to carry information, because you may happen to be in some areas where it is the signal intensity is very weak. So there are two ways we can think of improving this situation. One is if we increase the power of this transmitter enough so that we light up the entire room as we need. Or maybe we can think of what if instead of using one transmitter, we use a few of them and we distribute the power that we will use in one of them among the few of them. And then we end up with this fine-grained fabric of blue signal coverage. You can imagine if I had like a few of this across the room, and then they would increase the coverage. So it may happen that people already thought about this, and in particular in wireless sensor networks, we have a large deployment, we have a lot of nodes, so why not use them in a smart way to resolve this problem? So when we think of using this to convey certain information to be transmitted through this way, it will be convenient indeed that all these nodes are going to be transmitted. They have some sort of time synchronization, and the information that they are transmitted is exactly the same. Otherwise, we will have all the kind of things. So when we speak about constructive baseband interference, what we're saying is that the baseband signal that is transmitted from all these nodes is exactly the same. And of course, it's time synchronized accurate enough so that it's going to be constructive in the receiver. So people have thought about this. For example, this work, which was published in SIGCOM in 2010, shows how you can increase the radio coverage through sender diversity. So you increase the number. This is done for Wi-Fi networks. So you can have several access points that transmitting the same information, and the client, the computer or smartphone, have better coverage. And also they show that it has enhanced link, they can enhance link performance. There's another work, more recent in IPSN, where this Ferrari et al. Have shown that you can do this for low power wireless networks, and that will allow you to do fast flooding and with very low latency. And you can also have, as a side effect of using this technique, synchronization, sub-microsecond synchronization among the nodes. I will go back to this in a minute. But then we have also another work by Ferrari in 2012, where they show that if you use this technique to map the entire traffic of a wireless sensor network, instead of, it's a bit counterintuitive, because what they do here is to say, okay, so every node in the network will repeat the traffic of every other node, every packet, all the time. So it is counterintuitive, because if the objective of low power wireless network is to have energy efficiency, and then you make every node transmit what every other packet says at any given time, it seems like this is going to be a waste of energy. But what happens instead is that because they managed to synchronize, the most power-hungry component in the sensor node is the radio. So if you have very accurate time synchronization and you manage to wake up the radio right at the time that is needed to transmit or receive, and then go back to sleep, then you save a lot of energy. And so what they do here in this work is they end up with, at the link logical level, you don't have a wireless network with topology anymore. What you end up with is like a low power bus. It's a wireless bus where what everybody says is heard by everybody else. And then, of course, as a side effect of that, you get hassle-free mobility, because it no matter anymore where the node is, it will always hear every traffic, and it will also contribute to rebroadcast those packets. So just before moving on, I would like to make sure that we know how this thing works. I have a little explanation here, but this is about glossy. Glossy is this second paper here. We discussed this previously here. I don't know if you remember, but just for help understand how this works, I would like to go through it again. So let's say you have a wireless network here, and this is the initiator. So this is the node that wants to send some packet. And the objective is that everybody else, or maybe the intended receiver, is just one of the nodes. You're going to use the entire network for that. So this guy is going to transmit a packet, and all his neighbors, which are in radio coverage, they're going, this is the initiator, we will transmit this packet, and all the nodes which are neighbor to this, or which are in radio coverage, will be, alright, so I was touching something else. Sorry about that. So we get one packet transmitted here, and then all the neighbors over here that packet. And then what they're going to do, as soon as they hear this packet, is they will switch back to transmission, and they will retransmit that packet. And then this guy, which is the initiator, will hear that packet and will do the same thing. And they will, every node, as soon as he hears the packet, will enter into this loop, retransmitted the packet for a given number of transmissions. That this is something we specify to the project. Now you can see that as the nodes start to hear and retransmit, the message start to propagate through the network. Right? So, yes, please go on.
But how do you guarantee that the third hop doesn't listen to the first?
How do you guarantee?
How can you guarantee that both the third and the first hop can transmit simultaneously?
In order to do that, obviously you have to have time synchronization among the nodes. So what will happen is that, this is a good question, so you will bootstrap these mechanisms first until all the nodes synchronize. And once they are synchronized, then they can do this. Because they will know the time at which they have to wake up And even there might be before, this is just when you send the first packet. But you would expect the radios to be ready to repeat this cycle when you transmit again in the future. And therefore, it implies that when you transmit, they are already ready to listen. Because if this node, for example, were turned off, when you transmit, nothing will happen, right? So they will have to be time synchronized. Assuming that that condition holds, when this node transmits, it listens to the packet, quickly broadcasts, and then you see it is not only here back when traffic initiated, but it's also here in the next hop. Because this node, let's say that this node here is not on the radio coverage of the first hop. So what we have is this sequence that as soon as these guys start repeating, the message starts to advance through the network. And you can imagine a network with this large radius where this wave of information just propagates through. However, what it gets interesting is that when you have this situation here, where the initiator is repeating, but also this second hop neighbor is repeating as well, we get this situation here where the receiver is getting two signals that comes from two different nodes, and they contain exactly the same information. So you can think of it, if we go back to this picture, instead of having one single node here, which is the initiator, we have some other nodes here that at some point in time are going to participate in the transmission and convey the same information to one node that eventually will get it from this. Essentially, it's a node which is here. But if you have a redundancy and another transmitter here, maybe when the coverage of the two of them will cover all areas of the picture. That's what we want. We want to increase reliability and throughput by increasing the coverage through redundancy. Once that is clear, any question up to him? Are we all on the same page? So what we want to analyze now is what happened when we have this two-wave here colliding on the same node. And when we think of using this on real applications, unfortunately, this work is still kind of not only what I'm presenting here, but these other works that I've shown. This is kind of new, so we don't have large-scale deployments of this yet. And when we think of it, how to use it, we come up with we anticipate some problems under certain conditions, and that's what we want to study. We want to focus on how, when the signals are received here, if we have two signals colliding, or if we have n signals colliding, as it may happen that you have a dense network and you have a lot of nodes that participate in this retransmission, is it scalable? What happened there when these two signals meet somewhat? Because you see, if you look at it from the physics perspective, what you will see is that instead of having a simple superposition of all this wave when you put the other nodes in the work, instead what happened is that when this wave meet, they interfere with each other. And I'm talking about the carrier wave, not the interference. So we want to look at the scalability of the constructive baseband interference from the perspective of the carrier wave when they add up. And what we find, basically, we design some experiments to study this in detail. And what we find is that as the number of repeaters, the concurrent repeaters increase, the composite signal that is formed by all these nodes adding up becomes vulnerable to noise. And I will show soon why. And that, of course, compromises the quality, the reliability of the link. So that happens under a specific condition, and that is if there is not enough power imbalance between the participating nodes. When the power of those nodes are similar, then it happens that the composite signals become vulnerable to noise. And it's very fragile. It's very easy to get errors in the channel. And we want to avoid that, obviously, because that is harmful. That's not does not enhance the communication. So we have a simple model where we have this is the end senders, and let's suppose that they're going to transmit. It's going to add up in the wireless channel. and we will have a source of noise here. This is additive white Gaussian noise. And then we have the receiver. And then the signal that we receive is going to be the superposition of all those signals plus noise. And if we look into low power wireless networks, then what we have typically is, at least in 15.4, which is the standard in which most wireless networks operate, is something called offset quality phase shift keying, which may be familiar for some of you. And then the signals are more or less like this. This is the information you want to transmit, and the bits are interleaved. So originally you have like 1, 1, 0, 1, 1, 0, 0, 1. And you're going to do these tricks that I'm showing there with some mathematics, and you're going to 90 degrees phase, and you're going to transmit these two streams of beat at the same time. The reason you can do that is because the channel, you will use synchronous demodulation, which gives you two independent components which are linearly independent, and you can recover in the receiver. So that's what this cosine and this sine here does. The out of phase, and that allows you to transmit twice information. You have like, instead of one wireless channel, you have like two. So this mathematics here is simply to say, imagine the stream of bits that are coming from the past and to the future, and you can represent it like this. And these in-phase and out-of-phase components are going to be something like this. And then let's look how this is done. So this will be like the block diagram of a wireless transceiver, like typically used in low-power wireless networks. This is the receiver chain, and this will be the antenna here, and this is the transmitter chain. So in order to generate a signal like this, we'll have to first use a modulator that is going to create the signals. And then, in order to do that, we will basically use this quartz crystal here. And we're going to create a reference frequency, and then starting from that, we're going to multiply and divide that by different numbers to create the carriers that we need. And this is just to say that if you have this quartz crystal that has a certain, that is an uncertainty in the frequency that it will generate, because this is simply a piece of quartz that oscillates, but the frequency at which it oscillates depends on the physical dimensions of the quartz. So when you buy a quartz crystal, it will have a tolerance of what frequency accuracy you will expect. So this will say 16 megahertz, but then it will have obviously some bounds in which you will find those frequencies. And this is what the standard mandates, and it's perfectly fine. If you want to have this frequency, you see you divide it, and then you end up with 500 kilohertz, which, by the way, will have the same accuracy. It will be 40 ppm. Now, when we want this signal that we already generated, we want to put it on the antenna, we're still missing the carrier wave. And the carrier wave will be generated in this PL synthesizer. This actually what it does is multiplies the frequency of the quartz crystal by a very large number until you get the carrier frequency. In this case, it's 2,400 megahertz. And you get the simple mass here. But now there is something interesting. And that is because you multiply this frequency of reference that you created that is very stable, this is quartz crystal, and you multiply by this large number, and you get the frequency you want. This is what you're going to put in the antenna. But it just happens that as you do that, well, you had certain uncertainty in the frequency here, and that uncertainty translates into 100 kilohertz in this 2.4 gigahertz thing, right? That is a bit funny, and we'll see why. So, if we go back to the model, let's rewrite our receiver signal, which is we call this the composite signal. And you see this is superposition, and then we're going to write it, we're going to split it into in-phase and out-of-phase component. And then this is what we get, and we're going to focus now on the receiver. So this is what we have in the antenna of the receiver. We have these two signals, in-phase and out-of-phase. And then, of course, they're going to be multiplied in the receiver chain. The first things that they do is you get the same synthesizer that you used to transmit, and now you multiply those signals again by this carrier frequency in which you intend to receive. And the effect that it has is it translates these composite signals backward into frequency to baseband. And now you don't have a carrier frequency at the output of this. What you have is baseband. If you translate it back to baseband, if you multiply this signal here by this synthesizer, what it does in the frequency space, it brings you back to zero. If these two frequencies are the same, this and the collection. The problem is that if you look into this equation n equal 1, and then you have a single harmonic function here, then that's fine. That's how the radio normally operates. But if you have n transmitters, then what you get here is this superposition of harmonic signals with slightly different frequencies. And that produces beating. It's something called beating effect. I'm going to show you in a minute what it is. So when the amplitude of the signals are equal, what you're going to see is that the amplitude of the envelope will be depressed. And I want to give you some intuition on how that works. So you can see a mechanical model for that. I want to show you this. I think it's useful to help understand what's happening. So what I have in the picture is, this is, the bungee jump, right? So you get an elastic cord, and you have a mass, and you jump, and then you start to oscillate here, because you get potential energy, then it's kinetic energy, and you start going back and forth. So in this graph here, I'm showing, for example, the red arrow will be the position of one of the jumpers, and the blue one will represent the other one. But it just happened that because they have a slightly different mass, then they will oscillate with different frequencies. And that's what I'm going to do now. In this graph here, what we're going to plot is the sum of the two amplitudes of the oscillation. And you can imagine what is going to happen with the amplitude. Can you picture it in your mind? So let's do it slow. We're plotting when they are in phase, they're getting in phase now. When they are in phase, the amplitude is very large because it's the sum of the two. But when the frequency when the phases start to, because they're different frequencies, they rotate here with different angular velocity. When they're going out of phase, then instead of adding on, they're actually subtracting. And you get the result of the sum of this that you get is not something that is always with good amplitude, but sometimes depress and then go back and so forth. Can you see? Of course, that impacts because you see, now you can make the analogy. The frequency is like the quartz crystal of the different nodes which are different, and the resulting amplitude is what you would have in the receiver. So you no longer have something like a stable amplitude of one oscillating, but you get this. And these depressions, if you are modulating that with some information, and then it gets so low, and the noise corrupted, and then that is a problem. So you don't want that. So I have another example for you, but just to you get the picture. So let me show you another way to look at this, which may be useful. Oh, the core just broke.
I didn't get why they get this offset. So it's on the receiver side, not on the transmitter.
Okay, it's the transmitter. The transmitter is this.
Yeah, but why?
When you transmit, let's go back to when you transmit, you generate this current, right? But because the quartz crystal for all the participating nodes that are going to rebroadcast is not exactly the same. Then these currents are slightly different, right? But then when they sum up, because they're different, then we get to the beating. There's another way to look at it if you want to really. So you can hear that. That's the La note in music. It's 440 hertz, and this is slightly different frequency. It's 2 hertz apart, right? If we combine them together, right? This is with two nodes. Only saw the sample with two. But you can extrapolate that, and you can mine when you have many of them transmitting here together. What will happen is that if the amplitudes are equal, there is a point in time when, even though they have a slightly different frequencies, the phase will be so that all the amplitudes will add up, and instantaneously you will have like the sum of all these amplitudes. And there is a point in time where they will subtract totally, and you will have almost zero if all the amplitudes are equal or similar. So we have this situation now, and we want to study the scalability of this situation. I mean, what happens when we increase it? In order to do that, we design an experimental setup. By the way, when I'm showing this now, this is all the mathematics and stuff that we figured out after we solved the experimental problem. So the natural path for this study was not, we did not start here. We started when we imagine how it is, or we do the experiments and we see that it's not perfect, and then we start digging. So we are here. So basically what will happen then is that because this amplitude will depress, we have some noise here, and those instants of time, the information that is being conveyed cannot be received. Now, if that signal does not depress so much, and we still have a reasonable signal-to-noise ratio, then this demodulator will in principle be able to decode this information, or maybe it will decode it partially, and there will be errors. And that we want to study now. So how is all this parameter space, how does this play out? In order to do that, we're going to design an experimental setup, which is rather simple. We use some low-power nodes. Those are the nodes that will be doing this. But also, we want to look in detail into the signal, and in order to do that, we need other tools. So we're going to use a software-defined radio. By the way, this is part of the collaboration we have. We borrowed this radio from Etus. So they sell this equipment, but they had this deference to let us do experiments with them, with their hardware. We also have a customized additive white Gaussian channel. Notice that once we do this, and I'll show that in a minute, we get the signal into digital space. So instead of generating noise and put it in the wireless channel, what we want to do is we want to synthesize the noise in software and do these experiments of adding the different signals in a computer instead of actually in the wireless channel. And then we will use a transceiver, which is done in Doppler radio, that is interoperate with 15.4 technology, and that it means that it can actually decode the packets that come from the T-noise scan. And this is a paper from last year, I think, or 2 years ago. And so we had to extend this, and I will get to that at some point in the future. But this is more or less the basic experimental setup. We'll have this initiator node, and it's going to be transmitted at very low power. And then this guy is going to use a bit more power, but a bit better power. And all this signal goes into the software-defined radio. So why do we want to do things this way? Because we could actually be transmitting, like you would imagine that this will happen in the real scenario with antennas. What we gain with this is that we want to have a situation where we can control the amount of noise that we added systematically. And in order to do that, you can do that in the wireless channel, because you can control how much noise you have, and interference and so forth. So by doing this experiment in this way, we collect pure signal traces from this noise, and we add it up, and we get that, and then we're going to add the noise in software once we get this data into the computer. So in order to do that, you have to build this piece. This is basically a multi-port. Basically what this device is, it will get this carrier frequency, a very high frequency, 2.4 gigahertz, and it will give you a constant attenuation through all the ports. So you put a signal here, where you get the amplitude that you get here is all the same. And you can also guarantee that there is impedance matching, so there are no reflections. the signal. It's rather simple. Then we get here. So this will be this power combining that we showed. Then we will have the initiator. We will put this into the software-defined radio, and here then we're going to start adding noise and doing experiments. In order to do these experiments, what do we need? I mean, we want to study the error rate that is beating effects produced. And in order to do that, we're going to put information that is the information that is put in the payload of the packet that this node is going to be transmitted is null. And then we're going to, in software, look for the result of what we receive here, and we'll compare. And then we will do the statistics of how many errors do we get. Then this is what it looks like. This is voltage here in arbitrary units because it's not calibrated, and this is time. And if you make glossy functions on those nodes, and you look with an oscilloscope into the output of the SDR, then you will see this picture here. It looks more or less like this. This is the initiator. You can see that the amplitude is attenuated. And then this in here is when two nodes are transmitting concurrently. And it's right here where we want to pay attention. So the reason this is attenuated is because, as you can see, if we look to the signal, this will be the initiator. And you look at the complex baseband signal, and you see that because the information is in the phase, the amplitude is more or less the same. The magnitude does not change. It's not that is being modulated, what is modulated is the phase. But if you put two repeaters together, then we start to get this funny graph. And this is actually where we first started with this experiment. We saw this, and then from here everything else flew. So you can identify this. Does it look like something familiar now? So this is the baseband signal of two nodes that are transmitting together. They have slightly different frequency, and they start to beat. And you get these depressions here. If the amplitudes were identical, then this probably will completely depress here to zero. But it's not the case, and so you still have some signal. And if now we do the experiments where we transmit these packets, like hundreds of thousands of them, and we do the statistics, we get these curves. You can see this is chip error rate versus signal to noise ratio. These are the errors that we will find in the original transmitted packet relative, and this is the how much noise are we putting in. The lower the signal to noise ratio, the higher the noise, right? So theoretically what you will have is that for this kind of modulation, very quickly as the signal to noise ratio increases, the errors go down exponentially. And if you put one single node, then you get something pretty close to a theoretical curve. But if you start to put more nodes, so that they concurrently transmit, and the amplitudes are made the same, because they program to transmit to the same part, then we start to have these lane curves here, which actually say that there's a lot of errors. Even when you increase the signal to noise ratio a lot, you still get a lot of errors. And that's what's happening when the signal becomes so vulnerable when it has a depression that even a small amount of noise can interfere. But then and this is the reason of these widened experiments, is now we want to start to change the power level. So we want to say, okay, so how different so the power has to be before I start to have something normal again. And this give an indication. For example, we put in some nodes with -5 dBm and then -10 dBm, and you see this 5 dB power imbalance allows you to get the curves right back on track as you would like them to do. And the errors diminish quickly with the signal to noise ratio. Every time we measure one of these curves, it is only 2 nodes transmitting. Of course, it gets worse if you put 2 or 3 or 4 nodes. Okay, but that experiment is like a corner case. We are, constructed something there where we guarantee that the amplitudes are the same, and then we see this amount of error. But what should we expect to see if we had something more realistic, like with antennas and nodes transmitted? Right? And then we designed this other experiment. So we put these nodes, glue it on the wall. We put on the other side of the room the SDR with a computer, and we make them transmit, and then we collect again the same experiment. There's no wire now. They are operating on channel 26 where there is no much interference. So this is supposed to be like if you do these experiments like with Noda nodes, you would expect to have very good communication because they are just very small distance across. There is line of sight, there is no obstruction whatsoever. And but this is what we get. And now the things start to get intriguing. So this again, this is chip error rate. These are single error rates. It's slightly different because this is after you use there is some coding embedded into modulation to avoid to fight the multipass problem, and that's called direct sequences per spectrum. And basically what you do is you use that demodulator on top of the other one, and you recover the symbols, and that should give you better error rate than you will have if you don't use it. And what you sacrifice is data rate. You have lower data rate. But then this is what is actually useful, because now when you come here, this is when you have information. And you can decode the meaning of these. So now the power with which the both nodes are with all nodes are transmitted is the same. And we have, this is a theoretical again. The theoretical is not here, but it will be somewhere hidden down here. And this is when you have one single node transmitted, and we're going to start to increase the number of repeaters, like 2, 4, 8, and so forth. And then you see, if you have 2, then you still get kind of, well, it's not ideal, but it is somewhat reasonable. But when you put more nodes, then it becomes terrible. This is basically useless, right? And this is simply because we have, well, the scenario we have now 4 nodes transmitted here, and one other node on the other side receiving that. And how can that be? I mean, is something wrong in the experiment? Because it can get so bad. We look at the histogram of the baseband magnitude. That is when we have something like this. So this is the magnitude of the complex signal. You don't have information in the amplitude, you have it in the phase. But if you do the beating, then you observe the amplitude. You do like histogram, you wait for a long time and you see all the amplitude observations that we have seen. And this is counting the number of observations versus the amplitude that you observe. And then if you have a single transmitter, we can see this is sharp peak here, sharp peak, which contains almost same amplitude, and then you can this is cleaning up. If you have noise here, then you have enough signal to noise ratio, and you can decode the patterns. But as you start to add more repeaters, it just happened. For example, here you see the 2 amplitudes of them are not the same. Otherwise, this spike here would be 0. So they don't go completely depressed, but still. The observation says that it gets somewhat depressed. And this, when we add noise, relative to the peak of the signal. So then this area here will be vulnerable. And that's why we get some errors here. But you see, it's still reasonable. If we increase the number of repeaters, then when they beat the shoulder, this will become very messy. At some point, you get the whole amplitude of the sum of all of them, and in some other points, you see, this is bad. There is noise here. In a real channel, there is noise. So when it comes down here, you can decode signal, and this has happened too often in this graph. Okay, I can comment more on that if you have more questions, but that's basically what we look into. This is interesting because the scalability is, okay, so we have this constructive baseband interference, so we want to increase coverage. It's fantastic, yes, you can, instead of having one single transmitter, have multiples, and that increases coverage, but there are circumstances, and that is if you have those nodes, and for sure they will always have different frequencies as they originate in different oscillators. And then, well, there are some other works that I have cited have shown very good performance. They never saw the deterioration of the signal. And then we have this contrasting results where we see very bad and they see very good. And there must be some reasoning behind it. So we speculate that the reason that is happening is that those experiments that they have conducted are in very low noise environments. They don't add noise. And then there is also something interesting about this. If on the receiver side, after you transmitted this, let's say, messed up composite signal, you have a receiver that can dynamically adjust the gain of the amplifier chain to track this signal. Then when it comes down here, it will amplify a lot. When it goes here, it will de-amplify. And with that, if you have enough dynamic range, and you can do that with your amplifier change fast enough, then you can always be adjusting and you will never have signal that is too weak or too strong. However, when you amplify and you come to this quarter here, if you do have noise, you can amplify as much as you want, but you will also amplify the noise. So the signal to noise ratio cannot be altered by amplifying, and that is still a problem. So what do we do? I mean, you have this chromatin thing that has this problem here. When the amplitude of the signals are similar, then it performs very poorly. So there are two ways to go about it that has to be solved on the source. Once you receive the signal that is compromised, there is very little you can do. You hope that if there is no noise, you will be able to record, otherwise you have a problem. But then you can do something in the source. For example, you can think of, you can build up the pass loss map. So you have a graph of the network. And if you can know beforehand what is the pass loss that each of these links will bring, then you can probably try to do an optimization where you write the power allocation problem, how much power will I have to put on all these nodes, so that I guarantee that in every point where I have a receiver, there is enough power imbalance that the beating will be not so bad. And that would be like multi-objective optimization problem, where you will have to look into guarantee that all those points are enough and safe because there is not so much imbalance. But that is very interesting because then, of course, you can start to do many other funny things with it. I mean, we have to turn the problem around. This is a bad thing, how can we make it good? Well, you can think of, for example, you do this power allocation, you guarantee that all those nodes that you're interested in having the signal received have the right power imbalance, and then you can reuse some of the nodes in the network to transmit some noise or a corrupted signal in such a way that everywhere else except those points where you want to receive, for example, are going to be very difficult to decode a signal. And that will give you some side effect, which is that you avoid the stroking. So this is, we have been working on all this network for a lot of time, but now people start to get concerned about security. Like if you get Internet of Things and you get all those things running, can someone malicious can do something about it? So one way to enhance security is by avoiding that someone can eavesdrop. So before you can do something nasty about the network, first you have to know what's going on. And then there is another way, which in fact has already been tried, and this is a very common practice in wireless networks, which is that you use something called the space-time codes. That will pre-code the signal, because before you transmit it, in such a way that the amplitudes will not be the same, even they contain the same information. I'm not going into detail because this is a complex topic, but if you do that, then you require to go into the physical layer of the protocol stack and do modifications. So that is a problem for low power wireless networks because typically you don't have access to that because they're very simple radios. This is built up in silicon. And traditionally, for the past 10, 15 years, no one has access to that. this is changing. Now we do have low power, like we have low power radios that are suitable for this kind of thing because they do the physical layer processing with software. So there is an opportunity there if you really want to fix this in a different way than you can. Of course, there is so much stuff that you can do when you have access to a physical layer and you can do signal processing. So that's all I had to show. It was a lot of explanation, but actually very simple stuff. If you have questions, thank you.
So any question?
So I've seen some work on time synchronization or indoor localization, and they kind of trim the oscillator very precisely to avoid this offset. Wouldn't it work on this issue? Would it help?
Do you want to do localization?
No, I mean, because you're saying on power allocation or introducing this diversity game. What about playing with the oscillator, the timing?
Well, I see where you're going. You're saying, if the problem is caused by the frequency shifts in the oscillators, why don't we can do something about it? Problem is that even if you have, let's say for example, that you can, let's say that you can change the temperature, for example, in the oscillator in such a way that you correct the frequency just a little bit until you make two transmitters that almost have the same frequency. And then, as a consequence, when you get the beating, the frequency of this modulation here is actually the frequency difference between the two carriers. So if they are very equal, then this will be, they will still have it, but then it's very slow. So it will be like a bump here, very large, and then it will go down here, right? So what you can say, you can think of is, what if we manage to make them so tight that there is this big, long bump, and then comes the depression. But if the bump is so large, then I can put my packets in there and transmit and hope that, well, if you don't have, you cannot synchronize that, you can still hope that if you transmit, there is a chance that even if you don't put any coding in the packet, they know it. If you're lucky that it was transmitted, let's say for example that the duration of the packet is smaller compared to this one, and then you transmit and you didn't get through in the first attempt, maybe in the second one you do get through. There is a possibility you can think of doing that, but notice that even in the extreme case that you will have all those frequencies exactly the same, only possible theoretically. Then the problems that you have when you have this oscillating, this beating in time, you will not have it in time if the frequencies are exact, but you still will have it in space. This is how the small scale fading happens. So you will guarantee that if you are in this given point in space, the amplitude will always be this. I mean, you can think of a wave propagating. You can represent it in time, but you can also represent it in space, right? So there will be points where you can solve that. And in order to solve that, I mean, this is a core problem in communication systems when you have this constructive baseband interpret. It's used, for example, in digital television broadcast. Those transmitters that are used to broadcast digital television, of course they have much more resources than you can have in a sensor. So they can afford to do GPS type synchronization of the force, and they do funny stuff. But at the end, you will have, at the length of the wavelengths, you will have areas where they constructively add up and they destructively add up. And the only way you go about that is physical layer signal processing. So you end up recording the signal so they never have the same amplitude and you can still decode. So yeah, there is not much, I mean, there is, The opportunity for innovation here is when you ground the problem and you say, okay, I have these constraints. I don't have GPS time synchronization, or I cannot do physical layer coding. What I can do is, this will be a solution. If you say, my wireless sensor network is this cheap, and I don't want to complicate things. What can I do? Maybe you can say, okay, what if you switch this quartz crystal and you only make concurrent transmissions from nodes who you can pick in the network instead of having everybody broadcasting. You only make constructive with those that have similar frequency, in the hope that when you transmit, this bump will be so large that your packets will get through in the meantime. I mean, those things people can try those. But I think the thing is moving fast. Now that we have access to physical layer, it's going to be replicating the techniques that we use in other systems, and just making sure that they comply with the requirements of low power consumption and so on. Oh, it's tiring, yeah. Anyway.
Any other question?